GMGM. So in this series, we're going to do a light and breezy high-level overview of some of the elements that make SEDA's Oracle network different to a traditional Oracle. And as the name might imply, in network, we have a totally different design primitive that really flips oracles on their head from the way that traditional oracles work, which we would go into, and we'll talk all about that through this series. But the TLDR is that we built our own legacy Oracle and realized that they don't scale. They require deployments to new chains, complete infrastructure redeployment. So basically anything that you had to use for one chain, you then have to redeploy that to other chains. That means writing new smart contracts in different languages. It means audits, time, money, which is why traditional oracles really don't scale, and they require things like proof of traction to make it worth their while to go to new networks. SEDA was designed with all of that in mind, and the kind of bottom line of the design thinking was, how do we build an oracle that can horizontally scale to any network and can give developers access to any data that they need on the day that they need it, right? And so these are challenges that legacy oracles can't solve. So we had to build a new Oracle system, and that system is SEDA, and it's a programmable Oracle network. Let's start in the middle of the network, shall we, with the SEDA chain. And I am not an Excalibur maxi, but here we have SEDA chain. It's a layer 1 built on the Cosmos SDK. So what's the point of having your own blockchain as an Oracle network? So the SEDA chain acts as a data checkpointing sort of layer and a storage layer for data. In every block, you have data batches, and within every data batch, you have the data results from the ongoing or inbound requests that have been happening. And they live inside those data batches, and then anybody who wants to query any data on the SEDA chain can do so. So once data lands on the SEDA chain, it's accessible from all the other networks that are integrated into the SEDA chain, and we'll talk about how they integrate a bit later. But basically, any data that's live there becomes a bit of a marketplace, and they can query the chain, query the data batches, and get access to the data once it's been queried from its sources and landed and stored on the SEDA chain. So it's sort of storage, marketplace, checkpointing layer. And the reason that we call it a checkpointing layer is that because on the network, you actually have the SEDA decentralized validator set, which I believe is like 87 at the time of filming. And basically what the decentralized validator set do is that as the data requests come in, they get put into batches, which get stored into a block. As they're put into those batches, the validator signs off on them, and basically in that process, they wrap the batch and the block in a tamper-resistant proof. Now, why is that important? It's because if you just have data sitting unwrapped with this tamper-resistant proof, if you like, then when they're relayed by our solver network back to the network that needs it, essentially that solver could manipulate the data. So we kind of wrap it in this protection, this cryptographic protection, which stops the solvers from being able to manipulate data in transit from the SEDA network to whichever destination network. And then we have a thing called a proof of contract, which we'll speak about also, which decrypts the cryptographic proofs and then makes that data digestible on the decentralized, on the network that's receiving the data. So the TLDR here is the SEDA chain is the kind of data housing, storage, and checkpoint layer for data, and it sits in between the different parts of the network. So at the bottom we have the overlay nodes and the data providers, and they're responsible for the execution of data requests. And then above the SEDA chain, in this Excel drawer that I'm working on now, we'll have our solver network proof of contracts and obviously the data consumers. So it's kind of in the middle, and it separates the inbounds from the execution and then back.